So still important in E&M are forces in equilibrium and also work and energy. All right. Those you should have done in your mechanics class. Now getting into E&M. So basically we start with, there's a fundamental property of matter called charge. Or we call it charge, anyway. Right. And there's two types of charges. And we call those positive and negative. Right. It's a little bit different than, say, mass, right? There's a fundamental property of matter that we call mass, but there's only one type of mass, right? We don't have positive and negative mass. Charge is a little bit different that way. And we know there's two types because we've seen that like charges will repel each other. So if you have a positive and a positive charge, they'll repel. And unlike charges, attract. Right? And those are forces, right? That's a force. If you have two like charges, they exert forces on each other, repelling forces. And if you have two unlike charges, they're exerting forces as well, attracting charges. Right? And that might make perfect sense until you think a little bit harder, and you might say, but how do they force each other if they don't touch? Right? All the forces that you've probably studied so far, except for gravity, objects are touching each other. So, but how do charges force each other if they don't touch? Right? And the answer is fields. Right? These fields are what makes it possible to force without touching. Right? We've got two types of fields that we're going to be working with in here. All right, we've got the electric field. And you know a little bit about what vector fields are so far, right? These fields are vector fields. We've got the electric field, and that is created by charges. If you have a charge, you're going to have an electric field. And we're going to get into detail on how Coulomb's law creates an electric field from a charge. So the electric field is created by charge, but the other thing is that's equally important is the electric field affects charges. The electric field is what forces the charges. And I'll put that it's force. All right. And there's a little bit of weirdness there, because if you have something that's created by charge and then also affects charges, you can see how that might be a little strange. But it works out, and we'll get into the details as we go. This is really just like the gravitational field with mass. Mass creates a gravitational field, right? We know the Earth's gravitational field comes from the Earth's enormous mass, and gravitational fields also affect mass, right? They pull mass towards other mass. It's the same idea, and the equation is almost identical, as we'll see. Okay, we also have the magnetic field. We're not going to get to the magnetic field until a bit later. We start with electric. I can't talk and write at the same time. So we have the magnetic field, right? And the magnetic field is created. So the electric field is created by charges. The magnetic field is a little bit different. It's created by moving charges. If you just have a charge sitting in place, not moving, there's no magnetic field from that, but there's an electric field. And we also have the magnetic field it also affects which it means forces. Moving charges. So that means a moving charge, if there's a magnetic field there, is going to feel a force from that magnetic field. If a charge isn't moving and there's a magnetic field around, doesn't matter, right? Magnetic field is only created by moving charges, and it only affects moving charges. Right? That's really the only difference between electric and magnetic fields. And if you go in and learn relativity, you kind of realize that if you start moving relative to these charges, now the charge is moving relative to you, and electric fields can turn into magnetic fields and vice versa. But we're not going to get to that point for quite some time. Any questions so far? There's a nice symmetry there, right? The electric field is created by... Go ahead, sorry.
No, I was just saying my mind is like blown.
Good. Wait till we get to the end. It is a mind-blowing subject. That's why I really like it. The symmetry there is really nice too, and that's why I like to do this at the beginning, because if you can kind of keep this in your head, this is most of the class, right? The rest of the year is just getting into the details. Okay, so I'm going to go on to the next page here. Where was I?
So technically, electric fields and magnetic fields are made of the same thing.
Yep. Yeah. I mean, we don't, when you get deeper into physics, it's really electromagnetism, right? It depends on how you're moving. If you're moving really fast, right, then if I'm in a spaceship and you're sitting here on Earth looking at a stationary charge, as I've zoomed by in the spaceship, it looks like to me that charge is moving. I'm seeing a magnetic field from it. You're seeing an electric field from it. And it's only because we're moving at different speeds.
I see.
But the relativity part of it, we're not going to get to at least until after the AP test. That's when we get into relativity. But it's helpful to know. It's helpful to know that these things are really two sides of the same coin, right? Electric and magnetic fields are the same thing. One has to do with moving charges, and one doesn't. So we've got. Let's see. So the forces. Let me continue this. So the way the electric field is related to the forces is very simple, right? The force on a charge, the electric force, that's what this is just equal to that charge times the electric field. So if you know the electric field at a point, it's very easy to find the force on a charge at that point. Magnetic force. Right, and we use the capital letter B for magnetic field. So this is the magnetic force. I'll label it. This is the electric force. The magnetic force is only a little bit more complicated. It's the charge times the speed of the charge, right? We know it has to be moving, times the magnetic field. So the V is the velocity, the B is the magnetic field, I'll put over here, this E means the electric field. And what do you think the Q means?
Charge.
Charge.
Right, in both of those cases, Q is charge. I'll only label it once. So far, so good?
I just need to copy this down real quick.
Yeah, I can give you a minute. And that's kind of the easy part of it, right? What these two equations are is how the electric field affects the charges and how the magnetic field affects charges, right? If that's all it was, this wouldn't be a year-long class. It would be a 2-week-long class. Right? The more difficult thing is that first part is how the electric field creates the charges and how the magnetic field, how the electric field is created by moving charges. I didn't say that right. The harder part is how the electric field is created by charges and how the magnetic field is created by moving charges. So, and we're going to learn the simplest way, or the introductory way that an electric field makes, that a charge makes an electric field is through Coulomb's law. Right, which you've already seen if you've done the reading so far. This is we can determine the electric field from a point charge, a single point charge. Right, and that's the easiest electric field, is the electric field from a single point charge, positive or negative. But there's more than one charge in the universe, so we have to figure out what's going to happen to the electric field from more than one charge. So the next thing we'll learn is the superposition principle. That's not Coulomb's law. There's the superposition principle. And that's going to tell us how to determine E, or the electric field, from more than one point charge. Let's say multiple. From multiple point charges, or sometimes we call a bunch of charges a charge distribution. Slide that up a bit. I'm sorry, my handwriting is not very good. I don't think I'll be able to make it better.
Oh, it's pretty good.
Better than some of the students I've had, I know. And finally, we're going to learn Gauss's law, right? That's another way to find the electric field. around some certain, so this is a way to find the electric field from some simple, highly symmetric charge distributions. Right, like what if we have a uniformly charged sphere or
Move up the paper a little bit. I'm sorry for cutting you off.
No, that's fine. That's good. There you go. So Gauss's law will help us find the electric field from things like a uniformly charged sphere or an infinite plane of charge, which you might be like, well, why would we ever want to do that? But that ends up being useful actually in a bunch of pretty common situations. So those are basically the three tools we have for figuring out the electric field. Coulomb's law, the easy one, that'll figure out E from a single point charge. Superposition principle, that'll help us figure out E from a bunch of point charges. And Gauss's law, which will help us find E from some certain highly symmetric charge distributions. And you could get an electric field from a weird, highly unsymmetric charge distribution as well, but we won't have the tools to calculate that. Not in this class anyway. We have something similar on the magnetic side. We're going to learn on the magnetic side the Biot-Savart law.
The bio.
Biot, I'm not even sure if it's Biot or Biot. Biot-Savart law is what I usually say. And that will help us determine the magnetic field B from small bits of current. Right, and a current is just moving charges, right? So we'll learn the Biot-Savart law. The superposition principle is actually also going to apply to the magnetic side. So we also have, I'll just write superposition principle here again. And then finally, we're going to have Ampere's law. And that's going to help us find the magnetic field from some simple, highly symmetric currents, such as an infinitely long wire or a coil of wire called a solenoid. We'll have kind of Ampere's law and Gauss's law are shortcuts to find the electric and magnetic fields in those symmetric situations.
Is this where you get the word amp from this person's name?
Yep, yeah, and ampere is also the unit of current, and that the shortened name for that is amp. So yeah, absolutely. Good connection. All right. Okay, so the first thing to, or the next thing to be real clear about, these fields are real, right? These aren't just like mathematical constructs that we're using to help make this easier. These fields are real physical objects. The magnetic field, the electric field actually exist, right? And you might not believe that first, and maybe you probably shouldn't believe that yet if I haven't given you enough evidence for it. But hopefully by the end of the class, you'll see why that is. All right, these are real objects. We can't see them, but we can feel them. Okay. so I'm going to move on to another page here. We're getting through about 3/4 of the way done this. Okay. Where was I? Oh yeah. So both kinds of these fields, well, that's not true. Hold on. Electric fields, they can store energy and they can do work. All right, so we can store energy in an electric field, and we can use an electric field to do work, right? That is maybe to change that electrical energy into kinetic energy. So if you think about if there's a positive charge sitting there and I've nailed the positive charge down to the table, and then I take a negative charge, or let's say I take another positive charge and put it nearby, right? The energy that's stored in that electric field is going to turn into the kinetic energy of that second charge, right? It's going to shoot off and be repelled, right? So that's what we mean by the fields can store energy and do work. Magnetic fields, pretty much the same. They can store energy. But magnetic fields can't do work. Well, it's really because the direction of the force from the magnetic field is perpendicular to the direction that it's already moving. So you can use a magnetic field to change an object's direction, to change what way it's moving, but you can't use a magnetic field to speed something up or slow it down. And that we will see more about later. That's not a super important part of it yet. All right. Yeah, go ahead.
How come you can't slow things down with magnetic fields? Because I like an example I could be thinking of is a high speed moving object that has is able to be pulled by magnets and such, right? And it quickly moves by a magnet, like another magnet that has like the opposite polarity or something, right? Is that correct, or something like that?
Mm-hmm.
What happens when you have that magnet, and then like the north and south, we'll just say north and south, and you have north going that fast past south, is it possible for north to be going so fast that it ignores the pull from the south magnet?
So I'm going to have to hold off really on answering that. It's a subtle thing as to why they don't work. What I can say is if you do see an object kind of slowing down, then which is possible, then some other thing is going to be speeding up to compensate for it. Maybe the electrons orbiting the atoms in the object itself, or maybe something else.
Okay.
But the magnetic fields won't do any work, and let me wait a few months before we really get into the details of that. All right.
Okay. Cool.
Very good question, though. Very good question. So a little bit more about the energy from the electric fields. If you think about it, moving two like charges together, like charges together. Now that's going to take work, right? That's going to take effort to bring those two together because they repel. So moving two like charges together takes work, right? So what really happens there with the energy is that you're turning mechanical energy into electrical potential energy, right? The mechanical energy of the charge that you're moving turns into electric potential energy. All right. Then you've got the other The other way would be moving two like charges apart. That's going to release energy. Or really, I should say, when two like charges move apart, that's a release of energy. Right, in that case, the electric potential energy that's stored in the electric field changes into mechanical energy, really kinetic energy. So when you bring two like charges together, you're turning mechanical energy into electric potential energy. When two like charges move apart, that's electric potential energy turning back into mechanical energy. All right? And we know energy is always conserved, right, from previous physics classes, and that's always the case, here as well. And we're going to define one more term here. This has to do all with voltage, aka electric potential. And that's just the electric potential energy per unit charge. So when you're thinking about voltage, it's basically the electric energy per unit charge is all that it is. Questions about that?
So that's why. So voltage is the amount of charge that is possible to go through a system, right? Or a circuit.
Not the amount of charge that's possible. No, it's the amount of energy. So if you take a charge if you take a 1 Coulomb charge and you move it through a 1 volt potential, right? Then you're going to have 1 times 1 is 1. You're going to have 1 joule of energy either released or stored in the electric field.
Okay. Cool.
And we'll see more. Right, chapter 24 is basically all about voltage. So all we have left to talk about then are circuits, which is kind of an application of all this.
Pull your paper down or up, please.
Yep. So in circuits, there's really 4 circuit elements that we're going to be that we're going to look at. There are batteries, and that provides a potential difference. So that there is an electric field in the wire. Although that electric field goes away when the current starts flowing, but that's not important just yet. Right, if you take a battery out of a circuit, there's no more potential difference, so there's nothing to make the current flow, so nothing happens. You've got resistors. Right, and resistors can look like a lot of things. Light bulbs are resistors. You could have a heater that's a resistor. But what resistors do is they turn electric energy into heat or some other type of energy. Maybe mechanical energy, like if you're running a motor. Maybe electromagnetic radiation, if you're running a light bulb. Sorry, I'll write that over. EMR, electromagnetic radiation. right? A light bulb is turning electrical energy into light that you can see, as well as some heat that you can feel if you touch the light bulb. A basic, fan for your room that you put on in the summer, that's turning electrical energy into kinetic energy, right? Spinning the blades around. Your phone, right, is turning electrical energy into light that you can see.
So are heating systems made out of resistors?
Yeah. Well, yeah, especially if you have electric heat.
Okay.
If you have gas heat, then you're just burning gas. That's chemical.
All right. Great.
Then we've got capacitors. And capacitors are a circuit element that store energy temporarily, but they store energy in the electric field. And we'll see how once we get to that. And the final circuit element are inductors. And inductors will temporarily store energy in, can you guess what I'm going to put next? If capacitors store energy in the electric field, what's it make sense that inductors would do?
Magnetic.
field?
Exactly. Inductors store energy temporarily in the magnetic field. Great. So that's basically all there is to circuits. We get into detail looking at how the voltage affects the different energies that are given off of the resistors and everything. But that's the idea. And then finally, and we don't go into very much detail at all, or we don't really get into the nitty-gritty of it. But the best part is electromagnetism. So one thing we notice about the way that electric charges create electric fields and are affected by electric fields, and the way that magnetic fields are created by moving charges and affect moving charges, we get this kind of weird relationship here. A changing magnetic field produces an E field. And also, a changing E field produces a B field. If you have an electric field that's changing over time, there's going to be a magnetic field that comes from that. If you have a magnetic field that's changing over time, there's going to be an electric field that comes from that. So if you think about that, that means now you can have these electric and magnetic fields creating each other without any charge. So now charge is not even necessary for these electric and magnetic fields. Right, and it's something called Maxwell's equations that describe how this works. And you won't need to use them, but you'll need to kind of recognize them and know they exist. But now the best part, once we realize that a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field, and we don't even need charge anymore, we have a very good name for these electric fields that go back and forth, right? You can imagine you have this electric field changing into magnetic field changing into an electric field, and vice versa. And what you kind of get is this wave of this electromagnetic wave that radiates outwards. And what you have there is just called light. Right? All light and other electromagnetic radiation is just electric and magnetic fields oscillating back and forth in a wave and radiating outwards. All right, and that's it. That's all. That's the whole class.
Is that why lights can flicker?
Why what?
Is that why lights flicker? Like,
no, that's a little different. That would be, different. That's a different level of lights, depending on what your electric system is running. Because you can have light that doesn't flicker too, right?
Yeah, isn't there like a frequency for electricity?
Yep. Well, different Yeah, you can have these electromagnetic waves in all kinds of different frequencies. Yeah, and only a very small range of those frequencies are the light that we can see. This is the same process that makes high energy gamma waves, gamma rays, as well as X-rays, and also lower energy radio waves, microwaves, UV light, infrared. All of those are oscillating electric and magnetic fields. So other questions or comments on that? That's the end of the lecture for today.
Yeah, those notes fit perfectly.
Those notes really do fit perfectly on those papers that you have.
Yeah, that was pretty lucky. All right, I'm going to stop the recording now. So I'll put this up for you if you need to come and kind of refer back to it, because once we get into the nitty gritty, into the details, you can kind of lose sight of this big picture. But if you can keep this big picture in your head, it'll make the class, much easier. You always want to know why we're doing what we're doing, and I think this overview is helpful for that.